very much for the introduction and for the invitation. So this, what I'm going to present today is a joint work. The first part with Mohamed Lazaric, who is now in Northwestern University in Chicago, and I'm a Briscoe from CAU, and the second part with Nima Mar and Kamira Zadeh from UCI. So this is the attempt to explain what I mean by hidden world of bandits. So this is probably a picture that you've seen, but it's the reverse. So usually we have a huge iceberg below the level of the water. I reversed it because basically the idea of this talk is that oftentimes we have a lot of bandit problems or even reinforcement learning problems where we see a lot of different things. So the part that we can observe in terms of bandit problems, context, or observations in reinforcement learning is huge. But all of these hide somehow a very small structure that is hidden, so it's not directly observable. But hopefully I will convince you that there are some tools that can be integrated with bandit and reinforcement learning that can be used actually to reveal and to estimate this low-dimensional, smaller structure, and by doing that, being able to learn much faster and with much smaller regrets. And so the idea is, so can we learn structures and at the same time also finding, the bandit solutions or reinforcement learning solutions at the very same time? So I will start with the work which we have done a couple of years ago on sequential transfer with a finite set of multi-arm bandit problems. And I hope I will be able to move to the second part, which is a more recent work not published yet on learning in partially observable MDP, so a full reinforcement learning problem. So the idea is that oftentimes, we have bandit problem now. We have already seen what it is, so it's going to be, later during the day. At least I don't have to introduce much. So let's say that we have a student, we have to propose a bunch of different learning modules, so a bunch of arms, and we want to find the best one. So we run our favorite bandit algorithms, and eventually we will try to have the small regret as possible. Then a new student arrives, and we restart. And then another user arrives and we restart the game. So of course this you can generalize it to recommendation systems and so on and so forth. Now the idea is that basically it's probably a waste of time to try to restart your bandit strategy from scratch and not trying to somehow undisclose what are the similarities between these users, because maybe there is some similarity. Although notice that this is not a contextual bandit, so we don't know anything about the student. The student does not come with some features that can help us. It's a completely new problem, but maybe there is some similarity that we can exploit. And the idea is that although all of them at the beginning they come with a big question mark, oftentimes we can cluster them in a set of finite, for simplicity in this talk, finite set of types. So I will say that each of these bandit problems, each of these students, they come with a hidden type, which is not declared, is not revealed by a context. But hopefully by doing these bandit problems in a sequence, we will be able to learn these latent variables all over the way, contextually with the fact that we are learning also how to maximize our reward and so minimize the regret. And it's quite intuitive that if we knew from the very beginning these types, well, then we could speed up probably very much our learning strategy, because imagine that maybe I have 100 arms over which I have to optimize. Maybe there are just 10 different types. So in some sense, it's intuitive that I can exploit the fact that there are a finite number of types to switch from maximizing my reward and so minimizing the regret to try to identify basically the type of the current student, the current bandit problem. And this is exactly what we have done. This problem shares a lot of similarity with other works which have been done before and after our work, but this specific setting is quite peculiar. And I will show you what are the improvements that you can get. And in particular, what I would like to share with you as a message is that we can integrate traditional bandit strategies with latent variable model techniques and obtain fairly easily good results in terms of theory. So let's make the setting a little bit more formal. We have a finite set of arms, k arms, and I assume that I know from the very beginning the number of types, just the number, right? So this set of types theta, from theta 1 to theta m, it represents the type of users that I can encounter, and I know from the very beginning the number of them. I assume that there is a distribution which is unknown over the types, so every time I encounter a new student, it will be drawn from this set of types. And I will denote by mu I of theta the mean, so the expected value of arm I for the types theta, and the same for I star theta, which is the best arm, and the best value, which is mu star theta. Delta I of theta is the normal gap, so it's the difference between the optimal arm for model theta and the arm I. What is somehow specific in this case is this definition of the model gap, which tells me how different an arm I looks through two different times theta prime. And we will see that this is exactly the quantity we will scale with respect to. Okay, so the protocol is like follows. So it will be presented here in a fully sequential way. Actually, part of these users, these students, can be interleaved, but in order to make the theory a little bit easier, we'll consider the case where basically I have J episodes. These episodes are these little men that were appearing in sequence. Then I pick a specific identity of the type. I will also call task sometimes this theta bar J from the distribution. And then here I have just a specific bandit problem. So you can think about this as a bandit problem, and here I interact over n steps with it, and so I select the norm, I receive the reward, I update my estimates, and I keep doing it over and over both steps and episodes. So we will define the task regret, which is just the regret within this loop, so for one specific task, and then we will also consider the sequential one, so we will cumulate over episodes this per task regret. And you will recognize here the standard definition of the pseudo-regret, where here we have the number of times arm I has been pulled up to step n within the task J. And this is the gap that we defined before. So the objective overall will be to try to have the smallest possible global regret over episodes. And in order to make this somehow setting sensible, usually we will consider the case where n is small and J is large. In some sense, if n is already large, well, I can already learn a lot within each task. While if I have n very small, well, probably there's not much that I can learn about this guy, because I have to find the best arm very quickly. And on the other hand, I will be given a lot of students, in some sense, so that I can test my strategy and learn the hidden part fairly accurately. Okay, so let's start with just a strong assumption that we know everything. So we don't only know the number of times, but we also know exactly what is the value of each arm for each time. This is a totally unrealistic case, but at least it helps us in setting up a fairly straightforward algorithm that exploits knowing these times. So here we know for each time, we know the value of each arm. And now we have a specific user, so we don't know the identity of that user. We have to do the standard bandit algorithm, but incorporating the knowledge of the type. So we know that the current user will be one of them. We have some estimates, which I will call them mu hat IT. And instead of using just a UCB kind of strategy, we will try to integrate it with this knowledge in here. Instead of going through the formal definition, let me just give you an intuition. Imagine that these are the confidence intervals that you already constructed on your empirical means, given the samples that you observed from this very specific bandit problem. And these big dots are the values for the different types of users. So for instance, user green has this value for this arm, this value, this value. And for instance, this one, which is kind of brownish, type of user, we know that it cannot be the current one, because we know that these are high probability confidence intervals. So we know that the true mean of these arms will be within this blue bar. And so since we know that the brown type is outside, with high probability we can deem that we can basically claim that the current user is not of this type. And you can guess that this simplifies a lot our bandit strategy, because now we can just focus on the possible remaining types. And so over time we will restrict the set of active possible types which are compatible with our confidence intervals, and we will do a UCB strategy on the top of it. So this is a very, very straightforward algorithm, But of course, it gives a much better regret in the sense that we can drop a lot of uncertainty, which normally we would have between during the estimation phase. And so the normal log n divided by the gap bound, it becomes of this form. And I put here in red the two major improvements that we have. So one is here in the summation, you notice that there is this A+, which means that instead of, basically we can drop already some arms, which are not optimal for no matter which type. And so we can already restrict our focus on a much smaller subset of arms. And the other thing is that this term in here, which is, I have the explanation in the following of the slide, but the main message is that this quantity is always bigger or equal than the delta I, so the gap of the arm. So in a normal UCB strategy here we would have delta I of theta bar. In this case we replace it with this quantity which can be proved to be always bigger or equal. And yeah.
Can you use suboptimal arm to distinguish in which what's the type?
This is a good question. I think not. I mean, at least in this scenario, it doesn't give any improvement. But you can get up to. It depends how you do the analysis. In the sense that if you have different kind of assumptions on these models and how the mu I changes with the models, then you can exploit it and get even a constant regret. But that's a slightly different assumption. You need to know a little bit more a functional form of the mu I thetas. There is one of the papers that I studied that does that. Okay, so this is quite lengthy to go through all these definitions of the A+, this theta plus I, and so on and so forth. But again, the main take-home message is that we can restrict the summation over a smaller set of arms, and the regret per arm, in some sense, that we get, it's going to be smaller. But as I said, okay, this starts with the assumption that we know the types, and so this is really not the objective of this work. The objective of this work was to try to see whether I can estimate the types of the users online as I also learn how to solve the bandit problem in each set. And the way we do this is to integrate it with recent methods on spectral tensor decomposition for latent variable models. And here I will just give a rough sketch about how it can be implemented in our problem. So imagine that I define this random variable z, which is a k-dimensional vector, so one dimension per arm, which is obtained by sampling task theta type theta from the distribution rho, and then sampling a reward, which is IID by definition, from the distribution mu I of theta, so the distribution characterizing the arm I in the model theta. So this is for each component of this vector z. Now we have that the first moment is just the vector of all the mu's. So this bold mu is the vector with all the mu i's for all the arms. Then you can construct also the second moment, and the third moment. And the reason why this second and third moment are interesting is because just by exploiting the fact that the arms are independent with each other, because we have for each given theta the arms are independent, and from sampling for one arm, we obtain IID samples. What we get is this very nice rewriting. We can rewrite the second moment this way. So this will be just the tensor product. So here you can imagine just as a matrix, mu of theta transpose. But it's convenient because then for the third moment, of course, we get to a tensor. But the thing which is very interesting is that now you notice that this is a symmetric tensor. And you can imagine it as a decomposition, right? So it's just here you can think about it as a sort of SPD, and this is a decomposition of the tensor, so it's a kind of equivalent to an SPD for a matrix. And in particular, what we have is that then if we have good estimates of this N3, then doing a decomposition, it will allow us to recover this rho theta and these vectors mu of theta for each theta. So the intuition is really by exploiting very simple IID assumption on the arms and on the samples, and also on the fact that of course the tasks are not correlated, we can obtain this decomposition, and by first orthogonalizing it using this second moment, we can obtain just basically a unique decomposition of the tensor and reconstruct exactly all the terms that are unknown at the beginning. Of course, I said if you have estimates of n3. So first of all, we have to construct estimates of this n3. Now we go back to its definition. We see that it's the expectation of 3 independent samples taken from this generative model. But this is very simple in our case, because if I assume, but this is very trivial even to force, that each arm has been pulled in each episode at least 3 times, which any bandit strategy would do, what I can construct is at each episode L, I take for each arm all the samples that I have, I split them in 3 batches, and I construct this mu vector here, this mu tilde 1 for the task L. I basically take the first third of the samples, then the second third of the samples, the third third, and I obtain 3 independent batches. And at this point I can just construct empirical estimates of the second moment and empirical estimates of the third moment by just averaging out over episodes and taking these 3 batches for my independent estimates of the vectors mu. And at this point I just have to apply machinery to basically to tensor decomposition. First I make it an orthogonal, then we apply robust tensor, power tensor method to recover the eigenvectors and the eigenvalue, which in this case is the distribution rho. And then we can get basically good estimates of, so we get first good estimates of the n, and from there we get good estimates of the mu's. So basically these are the true mu's, the vector, the full vector for each model theta. And this up to a permutation, because of course the identity does not really matter. What we get is that our estimates converge with the rate which is of order of 1 over square root of j. So j is the number of users that I observed so far. And this statement basically tells me that my estimates will get more and more accurate in an L2 sense. I wanted to put here this expression that of course I'm not going to describe in detail, just to say, and I'll say that even later, that unfortunately these constants are not really known. This C of theta is not really known. It can be relatively small, but I will come back to it later if I get the chance. And so at this point, again, I will skip the formal definition of the algorithm. I will give an intuition. Basically, it means that not only we have our estimates of the current value of the arms for the current user, but we also come with an estimate of what are the values for the different times. Remember this green, red, and brown were the 3 possible types of users. And so now I don't have just one fixed dot, but I have confidence intervals, which I construct thanks to this latent variable model. And what I get is that some cases, for instance, like this, I can still discard this brown, because even considering the uncertainty I have with respect to that is not compatible with my confidence intervals. For some others, they will stay active even until the end, because I will always have a little bit of uncertainty about the true time. But thanks to these ongoing estimates that I have of the times, I can start approaching the performance of the algorithm mu the times in advance. And so this is basically the theorem when I have just j episodes, and so somehow it's a mixture between what I would get with the UCB and what I would get if I knew the types. So since I have some uncertainty, it's not as good as the one when I know the types, but it approaches that one asymptotically as I get j intrinsic. And this is exactly what happens also in practice. This is synthetic data, so of course it works very well on synthetic data. And this is what I would get over users with UCB on average, so over the expected user. This is what I would get if I knew everything in advance. And this is, over time, you see that I start approaching the performance of the algorithm that knows the types. Sure.
So it seems like there must be an assumption on the relation between k and m.
Correct. So the assumption here, I skipped it, it's in here, which is up there, is the fact that the types should not be, should be distinguishable in some sense. And so basically if I take this m by k matrix, or k by m matrix, it should be well, so basically the vectors mu theta should not be linearly dependent, which means that basically I don't have two types which expose exactly the same means up to a constant. This means that in some sense they are distinguishable. And so this forces n to be smaller than k.
I understand the point of the third moment because mu you can estimate it with the first moment, and then with the second moment, if you just do the eigenvalue decomposition, you will get the row. Right? But so usually you go to the third moment if you have only the second moment and not the first one, and then you want to, because the eigenvector are up to rotation.
Right. So first of all, given the first moment you cannot really you can estimate it in the sense that you have, but you don't know the theta, right? I mean, if I have user 1 comes, I have some estimates of its mean, but how do I attribute it to a theta? So it's not the lobes, right?
No. Yes, I see now.
It's a little bit tricky, but the fact that you move from the second to the third is that the second, again, up to rotations, it doesn't really give you the true mu theta, so you still have this rotation thing, and so you move to the third. But yet you have to orthogonalize it to make it at least unique, the composition. Okay, so I don't have much time, but I will still, first of all, I sum up on this. So this is, very quick, but it was just an attempt to show that we have a smooth integration, and you notice that I could apply just using at least 3 samples per arm, no matter how many more you have, but at least 3 samples per arm, which is not very restrictive assumption that I need. And the performance actually is never worse than UCB. So at each user, at least I perform as bad or as well as UCB, but over a task I will improve. And the main issues that the constants that I put in the confidence intervals for the types are not known in general. So it's in some sense it's a parameter to tune, let's say. And then that I still have to explore anyway all the arms all over the way, which we will see plays a big role, negative role in the coming example. And then there are questions. So for instance, I assume that I know the number of types. What if I don't know it? And then maybe is there a way to explore a little bit more on initial users to collect more data, to have better estimates of my models, so as to gain in regret later? This is a sort of open question at the moment. Okay, so I will go very quickly on this, but at least just to provide another example of how to integrate the spectral methods with reinforcement learning problems, so an extension of Bendy. The example that I give here is a little bit silly, but imagine a spoken dialogue system, so we interact with Siri or whatever, and we say, I would like to eat something, right? And imagine that I have a sequence of questions. So now it's not that I just have to find the best star, but I have to find the best sequence of questions, depending on the answer. So there is a state, it's really a full reinforcement learning problem. And so then I ask another question, and you reply sushi or something like this. And then another time, I might ask, how can I help you? I'm hungry. And then we have to relearn what is the optimal action when I observe that the state is hungry. Right? I have to learn the new action to do. But actually, both of these observations are hiding the fact that I'm in need of food in some form. And so this is a typical problem of reinforcement learning, where what we get is actually just an observation, but we don't get to see the real state. So the way I utter my needs, it might be very different, but down under, hidden somewhere, there is what I actually need. And so this is the hidden state. Usually, in order to formalize this problem, we use the POMDP, partial observable market decision process model. And in here, the definition is that we have a set of states, a set of actions, and we don't get to see these states, but we get just to see a set of observations, and we get the reward depending on the actions that we take, and depending on the state. So the reward that we observe is actually coming from the unobserved state. So this is the model that we consider. So this is the state. It produces an observation, so this is observable. I take an action. The action can only depend on the observation because I don't get to see the state. But the reward is due to my state and action pair, and it will also influence the transition over states, which in in turn will trigger the new observation, and so on and so forth. So this is a partial observable model, and it's well known that if I know what are these models, so how the rewards are generated, how the transitions happens, and in particular how the observations are triggered, then I can learn fairly decent policies, even if I don't consider history-based policies, but even just stochastic memoryless policies that perform pretty well in this case. The problem is that, once again, I have no knowledge about what are the hidden states, and actually what is the model generating my observations. And so, once again, the idea is to integrate it with, so I will skip through a few definitions just to give a hint about how this can actually be done. In the sense that now we don't have a simple problem as the one before, where we get these independent arms. Now, I showed you that we have strong correlations between the states, the observations triggers my action, and my action triggers the evolution of the state. So things here are very little independent, but yet you can construct a sort of multi-view model over it, and being able to reconstruct this procedure of tensor decomposition. So let me illustrate rapidly the idea. Imagine that I fixed a policy. So I run a policy for a while, and now for each action, I consider all the times when I use this action, L. Now I can construct these observations here, these views, which are the previous action, previous observation, previous reward, current observation, and sorry, this is RT, current reward, next action, next observation, next reward. And the very funny thing is that now if I consider these three variables, vector variables, the nice thing is that once I condition on xt, so the state time t, all these three views, they become independent. So this is not fully apparent when you look at it for the first time, but they're actually independent random variables. And so this is very helpful because we've been able to recover, to some extent, independent observations of the hidden variable x2, so the xt in this case. And so thanks to this, we can still apply the idea of the spectral decomposition of the tensor. So we construct now tensors on these variables. The thing is a little more technical and more complicated. But basically, over a full trajectory, we will be able, over time, to improve our estimates of the underlying model, of the observation model in this graphical model here. And so as much as we are learning in a reinforcement learning standard way, so we will integrate it in this case with the UCRL strategy instead of UCB, over the UCRL strategy, we take advantage of the estimates that we have about the parameters of the PONDP, and we will be able to construct, again, a simple integration even from a theoretical point of view, showing that the regret, we will approach the optimal policy as if I knew the actual PONDP structuring here. So I think I'm a little bit over time, so I will, this material is over, it will be over the web later. And so basically the take-home message in here is that although we have a lot of these kind of problems, and notice that I here put context also because it could be extended to contextual bandit as well, where you have a lot of context for few hidden states. I advocate the fact that in many cases these new techniques of spectral tensor decomposition for latent variable models can pretty smoothly be integrated with multi-arm bandit or reinforcement learning strategies, and being able to basically integrate also the theoretical guarantees together and achieve small regrets as if we knew the hidden structure down here. Thank you very much.
Thank you.